Second part of chapter 6, we're going to discuss the element stiffness metric. The element stiffness metric is derived by using the potential energy approach. The strain energy of an element is given by this equation, where it's a half integration of strain multiplied with the material properties and the strain, thickness, and dA. From the previous chapter, we had defined that the strain is equal to matrix B times U. And if we replace this term into the previous equation, we're going to have this equation. By solving the integration of delta TA here, that gives equivalent to area, then our equation of the strain energy is given by this equation. By comparing to the force displacement curve, where the area under this curve is actually the strain energy given by this equation, half K times U square. This equation we can rearrange so that we can have a term half U times K and U. If we compare between these two equations, we can see that in this equation we have U, we also have U here, U at the back, and also U at the back, meaning that the middle part is the K value. So we can conclude that the K value is actually this term, as shown in this equation below here, where U is the displacement or the degree of freedom in one element from U1 until V3. The D is the material matrix or the material properties. There are two types. One is for plane stress, one is for plane strain. The matrix B is given by this matrix. T, as mentioned, is the thickness of the element. A is the area of the element, the surface area, or either you can calculate manually using half time base time height, or we can use this equation if the shape of triangular element is very complex. And J is not a Jacobian matrix, so normally this J, we use this J in order to calculate the A. Okay, so for one element, the K matrix is given by this equation, where when we expand this equation by including all those parameters, matrix B, matrix D, matrix B, and so on, so we're going to have this general K matrix with the plane stress or plane strain. We're going to use the same K matrix. The only way to differentiate between plane stress and plane strain is the value of the material properties, which is D11, D12, D33, where for plane stress is using this equation, while for plane strain we are using the bottom equations. So the next thing that we have to know in order to use this matrix is to determine the value of x13, x12, and so on. So x13 means that x1 minus x3. y12 meaning that y1 minus y2. If let's say x31 meaning that x3 minus x1. So it must follow this equation. The bottom part here, dB, so this matrix normally is used for stress calculations that we're going to discuss later on. We consider the previous example. This time, we are required to obtain the global reduced stiffness metric for this problem. From the previous example, we have decided the shape of triangular elements. We have decided the type of problem, which is plane strain. Next, the first step in order to determine the reduced stiffness metric is to determine the material properties. So given in the question, the modulus Young is 20 gigapascal and the mu is equal to 0.4. By using the equation that dedicated to plane strain, we can determine the value of D11, D12, and D33, as shown in this slide. For plane strain problems, sometimes the thickness is not given. Therefore, we have to assume the thickness. We can assume any values like 1 meter, 1 millimeter, 10 millimeter, any value as long as the value that we choose is consistent throughout our calculation. In this problem, I assume the thickness is equal to 1 meter. The third step is to obtain the reduced stiffness metric for each element. Let's start with element 1. The first thing that we have to do is to determine the element connectivity. For example, in this case, I connected the element by using node A, B, C. In fact, you also can connect the element by using node B, C, A. Or you start with C, A, B. It doesn't matter, as long as it follows the sequence of counterclockwise rules, as shown in this slide. In this case, I just follow the sequence of A, B, C in order to make our calculation easier later on. Once we have decided the element connectivity, then we have to number the nodes with 1, 2, 3. Meaning that the coordinates of node A will be x1, y1. Node B, the coordinate will be x2, y2. And node C, the coordinate will be x3, y3. Then, the next step is to determine the surface area of this element. I just simply use the formula half times the base times the height, which is equal to the value as shown in this slide. As we connected the element with node A, B, and C, then the arrangement of our K matrix must also follow this sequence. Therefore, our row and column must start with UA, VA, UB, VB, and UC, VC. And please remember, always start with displacement in X direction, followed by the displacement in Y direction. Next, as we already determined the boundary condition in the previous video, therefore for element 1, we know that UA, VA, UB, VB are equal to 0. Then we can eliminate the row and column of this 0 value degree of freedom in order to obtain the reduced stiffness matrix. After eliminating those unwanted rows and columns, there are only 4 terms left as shown. We can name this term with A, B, and B again, because this value is symmetrical to this term. Okay, that's why we put B as well. And the last term is C. Please take note, do not forget this term, the one that outside the matrix, in our calculation later on. In order to determine the value A, B, and C, we have to refer back to our coordinates determined for element 1. For example, x1, y1, x2, y2, and x3, y3. We also need the calculated material properties in the previous slide, which is D11, D22, D12, D21, and etc. as shown in this slide. To simplify our calculation, it is better for us to calculate this term T over 4A, which is equal to 1 to 5. Then we just need to calculate the term A, B, and C according to the formula given in the matrix. For instance, the first term A, we have to determine this value first, y12 and x21, according to this formula shown above this slide. Refer back to our coordinates. Y1 is equal to 0 and y2 is equal to 0. Therefore, y12 is equal to 0 minus 0 equal 0. Thus, we can eliminate this term. Next, x21. Refer back to our coordinates. x2 is equal to 0.1. x1 is equal to 0. Therefore, x21 is equal to 0.1 minus 0 equal 0.1. Then, we just need to substitute the value D33 into this equation and calculate. We obtain A is equal to 8.93 times 10 power 9. We apply the same method for B and C. And we obtain the value. Once we obtain all the value of A, B, and C, we can write our reduced K matrix for element 1, as shown in this slide. Now, let's move to element 2. Similarly, we have to determine the element connectivity at the first place. For this element, I created it by connecting the node A, C, and D, which is still follow the counterclockwise rules. Therefore, node A is numbered with 1, node C with 2, and node D with 3. Thus, for element 2, the coordinate A will be x1, y1. Node C, the coordinate will be x2, y2. And coordinate D will be x3, y3. And next, similarly, we have to calculate the surface area of element 2. In this case, I took this side as the base and this length as the height of the triangle. Therefore, the surface area is equal to half times 0.1 times 0.08 equal 0.04 meter square as shown. Again, as we connected element 2 with node A, C, D, then the arrangement of K matrix for element 2 must also follow this sequence. The row and column of K matrix 2 must start with UA, BA, UC, VC, and followed by UD, VD. Next, similarly, as we already determined the boundary condition in the previous video, for element 2, we know that UA, BA, and UD are equal to 0. Therefore, we can eliminate the rows and columns of these 0 values degree of freedom in order to obtain the reduced stiffness metric for element 2. After eliminating those unwanted rows and columns, there are 6 terms left in this matrix. We can name this term with A, B, and C, followed by B again, as this value is symmetrical between the term K34 and K43, followed by D, E, and again C, as this value is symmetrical to the term K36 equal to K63, and E again, as this value also a symmetrical value between the term K46 and K64, and the last term with F. Again, please take note, do not forget the term outside the matrix in our calculation later. In order to determine the terms left in the K matrix 2, we have to refer back to the coordinate of nodes in element 2 in order to know the values x1, y1, x2, y2, and x3, y3. Besides that, we also have to refer back to the calculated material properties such as D11, D22, D12, and etc. as shown in this slide. Again, to simplify our calculations, it is better to calculate this term, the one outside the K matrix, which is T over 4A. In this case, this value is equal to 62.5. Then, similarly, we just need to calculate the terms A, B, C, D until F according to the formula given in the matrix. For instance, the first term A, in this case, we have to determine the value y31 and x13 at the first place. In this case, y3 is equal to 0.08 and y1 is equal to 0. Therefore, y31 is equal to 0.08 minus 0 equal to 0.08. While for x13, x1 is equal to 0 and x3 also equal to 0. Therefore, x13 is equal to 0, and we can eliminate this term in this formula. And then we just need to substitute the value D11 into this equation. We can determine the value for term A, as shown in this slide. By applying the same method for the rest terms, we can determine all those values according to the formula given in the matrix as shown in this video. Once we have obtained all the value A, B, C, D, E, and F, we can write our reduced K matrix for element 2 as shown in this slide. After we determine the reduced K matrix for element 1 and element 2, the next step is to assemble the reduced global stiffness matrix as shown in this slide.